In this session, we're going to see how to find inverses of matrices, but first, some background. If we consider the number 3 and subtracting the number 3 from 3, then of course we get a result of 0. Another way of looking at what just happened is we took 3 and we added to it its opposite, and that gave us that result of 0. The opposite, in this case when we add it, is called the additive inverse. And when we add a number to its additive inverse, we get the identity element for addition. And it is so named because when you add it to something, it doesn't change its identity. We use this idea whenever we solve an equation. For instance, x plus 3 is equal to 5, and we subtract 3 from both sides. Technically what happens is we end up with x plus 0 on the left-hand side, and because 0 doesn't change anything, we have essentially isolated the variable that we were after. A similar thing happens with multiplication. In fact, if we take 3 and we divide it by 3, we get the answer of 1. Well, this is akin to taking 3 and multiplying it by the reciprocal 1/3, right? So this is how they're exactly parallel. And we get 1. In this context, 1/3 is the multiplicative inverse of 3, and 1 is called the identity element for multiplication, because it's the value that when you multiply it by something, it doesn't change its meaning. And we see this whenever we have something like 3x is equal to 15. One way to look at what we're doing is we're dividing by 3 on both sides. Another way to visualize what's going on is that we're multiplying both sides by 1/3. And on the left-hand side, when we multiply by 1/3, we end up with 1 times x. And of course, on the right-hand side, in this case, we'd have 5. And 1 being the identity element for multiplication means that we have now essentially isolated the x. So these are kind of details that we don't necessarily think about much. Here's another one we don't think about very much. Here, when I multiplied by 1/3 on both sides, on the left-hand side, I multiplied by 1/3 on the left because I wanted it next to the 3. On the right-hand side, I multiplied by 1/3 on the right because that's where I had room. We get to do this because multiplication is commutative, right? We can switch the order of the factors and end up with the same product. That's not true with matrices, and so when we start to apply this to matrices, we're going to have to be careful where we put the matrix that we're multiplying by. But we'll get to that, in fact, in a different session. Now, putting these ideas together with the idea of matrix multiplications, if we had a matrix equation, a plus x is equal to b, if I wanted to solve for the matrix x, I would simply subtract the matrix A from both sides. No big deal there. But if I have an equation A times x is equal to b, then what I want to do is, really I want to divide both sides by A, but I don't get to do that. What I need to do is I need to use a multiplicative inverse so that I can end up with an identity element for matrix multiplication. As it turns out, the identity matrix in the 2 by 2 case is 1, 0, 0, 1. The 3 by 3 identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. If this is looking a little familiar, it's what we're going for whenever we solve a system by using augmented matrices. This 2 by 2 identity matrix is referred to by using an I subscript 2. And then I sub 3 is the 3 by 3 identity matrix. Notice they're both square matrices. The n by n identity matrix is denoted I sub n, and the way we write it is we put ones down the diagonal, and we end up using a dot, 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 because we don't want to try to declare how many positions there are. The upper right triangle is a bunch of zeros, and the lower left triangle is a bunch of zeros. So we draw large zeros there. It's ones down the diagonal and zeros everywhere else. Now, just as adding a number and its additive inverse gives the identity element for addition, and multiplying a number by its multiplicative inverse gives the identity element for multiplication, multiplying a matrix by its inverse, and it's going to be denoted using inverse function notation actually. So a times a to the negative 1 is what it looks like, is equal to I sub n, the identity matrix. The way this is going to play out is if we have a matrix equation AX is equal to B, if I multiply on the left by the identity matrix on the left, then I have to multiply on the right-hand side of the equation by the identity matrix on the left again, right? Because matrix multiplication is not commutative. But this A inverse times A becomes the identity matrix, and we have now isolated the matrix X. And on the right-hand side, we have A inverse times B. This session is not about all of this. This session is only about the inverse itself, finding it, and seeing just what it means to have an identity matrix. And we're first going to start with that identity matrix idea. So for our first example here, let A equal the 2 by 2 matrix 2, 1, 3, negative 5. Multiply I sub 2A and A times I sub 2. I2A is 1, 0, 0, 1 times the matrix A, 2, 1, 3, negative 5. And A times I sub 2, it just reverses the order, 2, 1, 3, negative 5 times 1, 0, 0, 1. What I want you to do is pause the video and multiply each of these pairs of matrices together. You notice in both cases we recover the original matrix A. That's the meaning of the identity matrix. You also notice that we were able to commute these, the I2A and A times I sub 2. That's the case when we have an identity. Multiplication there is commutative. In general, matrix multiplication is not commutative, but when you got special stuff happens. Now we move on to the 3 by 3 case. Let B equal the 3 by 3 matrix 3, negative 4, 1, negative 9, 7, 6, 8 pi E. Multiply I3B and BI3. So remember that I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. And I want you to go ahead and perform both of these multiplications. Pause the video and then come back. And hopefully by now you're seeing how the ones and zeros work together to give us back the matrix that we started with. In other words, in this case, B each time. Now I want to move on to the idea of what we've already seen. If I multiply 3 by 1/3, then I get 1, right? If I multiply A by its inverse, A times A inverse, then I'm going to get an identity matrix. Generically, I can say A times A inverse is equal to I sub n. As I said, this is a fact that we're going to use in a future video, but right now, what we're going to do is find inverse matrices. The way we're going to do it is we're going to set up an augmented matrix with A on the left and I sub n on the right. We're going to perform row operations as though we were solving a system using augmented matrices. But in this case, when we end up with I sub n on the left, we're going to end up with A inverse on the right. And so it's like solving a system with augmented matrices, except on the right side of the vertical line, you have a lot more entries. I want to note that multiplying a matrix by its inverse, or multiplying by an inverse matrix, I should say, is the closest that we can come to dividing by a matrix. You can't divide by it, but we can multiply by its inverse. And we should make a note. A inverse only exists if A is a square matrix. That is not to say that all square matrices have an inverse, but that is to say if our matrix isn't square, don't even bother trying. When I say square matrix, I mean like 2 by 2, 3 by 3, etc., right? It's the number of rows has to equal the number of columns. Well, let's see how we can find the inverse of a matrix. We're going to let A be the 2 by 2 matrix, 2, -5, 3, -6, and we're going to find A inverse. So we set up the augmented matrix, 2, -5, 3, -6, vertical line, 1, 0, 0, 1, and we're going to perform row operations to turn what's on the left into the identity matrix. In other words, we want a 0 in the lower left corner, a 0 in the upper right corner of the matrix on the left-hand side, and we want 1s in the bottom right corner and the top left corner. So go ahead and do that, and then come back to the video. So first I'm going to replace row 2 by 3 times row 1 minus 2 times row 2. I end up with a matrix 2, -5, 1, 0, and then 0, -3, 3, -2 with a vertical line separating the two matrices. Now I'm going to replace row 1 by -3 row 1 plus 5 row 2. And my new row 1 now is -6, 0, 12, -10. I haven't changed row 2, so 0, -3, 3, -2. And now it's going to get a little bit squirrely because we're going to take row 1 and since the first position is -6, we're going to multiply by -1/6 of row 1. Right, so we're going to cut it down to size and make sure that the leading number is 1. Likewise, we're going to take row 2 and replace it by -1/3 times row 2. And the result of this is 1, 0, -2, 5/3. You see that fraction there? That's why I don't do this division and get ones until the very end. Then the second row is 0, 1, -1, 2/3. Folks, I see this every semester that I teach this. There's no reason for you to get fractions until the very last step. If you're working with fractions while you're performing various steps, you're making harder work for yourself. I don't care what any tutor tells you, wait until the very end before you get your zeros, unless you just like poking yourself in the eye a lot. The result of all of this, though, is that A inverse is the matrix that's on the right. And so A inverse is -2, 5/3, -1, 2/3. That's our inverse. How do we know that what we've done is correct? Well, I'm glad you asked. Now what I want you to do is verify that A inverse is the inverse of A by multiplying A times A inverse or A inverse times A. Since we're dealing with the inverse, if I get the identity, then it would work both ways, which is why we only need to verify one. Some books will say do both. I don't know. If you want to, go ahead. In any case, I know what the answer is going to be, so I'm going to go ahead and move on, but you should take responsibility for your education. Go ahead and pause the video and do that. I'm going to move on to this next example. Show that the matrix -3, 1/2, 6, -1 has no inverse. Since it's a square matrix, I don't get to say, oh, the dimensions don't match, so it can't. All I can do at this point is go ahead and try to find an inverse. So I'm going to set up my augmented matrix. -3, 1/2, 1, 0, 6, -1, 0, 1. And then perform row operations. I'm going for a 0 in the lower left corner. And so I'm going to replace row 2 by 2 times row 1 plus row 2. Let's see what happens. I end up with the bottom row of 0, 0, 2, 1. As soon as the entries on the left of the vertical line are all 0 in a row, then I know that no inverse matrix exists. So when you zero out a row, or one side of the line, the vertical line, when you zero out that part of the row, then you'll never recover a 1 and leave the other one as 0. And so this is done, showing that we have those two zeros is sufficient. And the vocabulary for a matrix that has no inverse is that it's non-invertible or singular. Okay, so if we can find an inverse, it's invertible. If we can't, it's singular. I know. Get used to the vocabulary. For our next example, let B be a 3 by 3 matrix, 3, 3, 1, 1, 2, 1, 2, negative 1, 1. Find B inverse and verify by multiplying. Go ahead and pause the video and do that. So I've replaced row 2 by row 1 minus 3 times row 2. I've replaced row 3 by 2 times row 2 minus row 3. I end up with 3, 3, 1, 1, 0, 0, 0, negative 3, negative 2, 1, negative 3, 0, and 0, 5, 1, 0, 2, negative 1. Now I of course want a 0 in the middle position in the bottom on the left, and so I'm going to replace row 3 by 5 times row 2 plus 3 times row 3. My new row 3 is 0, 0, negative 7, 5, negative 9, negative 3. And now I want zeros in the first and second rows, third positions on the left side of the vertical line. And as it turns out, when I do both of those things, I was able to divide each of those rows by 3, which is something we're allowed to do in augmented matrices. And I end up with a new matrix, 7, 7, 0, 4, negative 3, negative 1, 0, 7, 0, 1, 1, negative 2. And the third row is unchanged at 0, 0, negative 7, 5, negative 9, negative 3. Now I'm after a 0 in the top middle position of the matrix on the left of the augmentation. And so we're going to take row 1 and replace it by simply row 1 minus row 2. And we're going to end up with a new first row of 7, 0, 0, 3, negative 4, 1. And the second and third rows are unchanged. And now, since I want 1s down the diagonal and not positive and negative 7s, I'm going to replace row 1 by 1/7 times row 1. Row 2 likewise by 1/7 times row 2. And row 3 by negative 1/7 times row 3. And lo and behold, I end up with the identity matrix I sub 3 on the left. And on the right, I have the inverse of B, which turns out to be 3/7, negative 4/7, 1/7, 1/7, 1/7, negative 2/7, and negative 5/7, 9/7, 3/7. Our instructions were to find this and verify, and so what I want you to do is multiply B inverse by B and make sure that you come up with the identity matrix. I am moving on, which is to let A equal a 2 by 2 matrix, 2x, x, x squared. And we're going to find A inverse. And then there's an additional question that will make sense after we do this. For what value or values of x, if any, does the inverse of A not exist? Well, this starts out the same way. We set up an augmented matrix, 2x, 1, 0, x, x squared, 0, 1. And our steps are the same. We want a 0 in the lower left corner, a 0 in the upper right corner of the matrix on the left, and then we want 1s in the other two positions down the diagonal. So this is kind of like finding least common denominators, as a matter of fact. What we are first going to do is replace row 2 by, let's see, if I multiply row 1 by x, and then subtract 2 times row 2, then my coefficients will be 2x and negative 2x, or my entries. And that would end up giving me a 0 where I want it. In other words, we have 2x, x squared, x, and 0 from multiplying row 1 by x. Multiplying row 2 by negative 2 gives me negative 2x, negative 2x squared, 0, and negative 2. Adding these together gives me 0, negative x squared, x, and negative 2. In other words, I have the 0 where I want it. That's our new second row. Our first row is unchanged. And so I have 2x, 1, 0, and then 0, negative x squared, x, negative 2. In the first row where there's an x, I want a 0. And so it seems to me that if I take row 1 and multiply it by x, and then add to it row 2, we're going to annihilate that x, and we're going to get a 0. So we're going to replace row 1 by 2x, x squared, x, and 0, added to 0, negative x squared, x, and negative 2. Adding those together gives me 2x, 0, 2x, negative 2, right? We're just combining like terms. That's our new row 1, 2x, 0, 2x, negative 2. I guess I could divide out by 2, but it doesn't matter at this point. And row 2 was unchanged, 0, negative x squared, x, negative 2. Now I need to get 1s down the diagonal. In the first row, I have a 2x where I want a 1. So I'm going to replace row 1 by 1 over 2x times row 1. See, I'm dividing out the 2x. In the second row, I have a negative x squared where I want a 1. So I'm going to replace row 2 by negative 1 over x squared times row 2. And I end up with 1, 0, 1, negative 1 over x, and 0, 1, negative 1 over x, 2 over x squared, which then gives me that B inverse is the matrix on the right, 1, negative 1 over x, negative 1 over x, 2 over x squared. So that's what we were supposed to do, find the inverse of B. We were also asked to say where these don't exist. This exists as long as x is not 0. So I'm going to say it exists for x not equaling 0. The reason is we can't divide by 0, right? I recommend that you verify that this is the inverse by multiplying B by B inverse. Before I end this session, a note. Someone may tell you, hey, there's a trick for finding the inverse of a 2 by 2 matrix. And it's true, there's a trick. It only works for 2 by 2 matrices. I'm not going to show it to you. It involves something we haven't actually seen just yet. This process of converting the matrix on the left to 1, 0, 0, 1, and likewise for the 3 by 3 case, and it would work also for the 4 by 4 case, the process I'm showing you works for all matrices for which there is an inverse. I don't like to show people tricks that work for only particular cases. That said, if you know what it is and you want to use it, go ahead. I'm just not going to show it to you.